Earth's magnetic field is fading. Recent findings suggest that over the last 3 millennia, our planet's protective shield has lost nearly a third of its strength. This invisible fortress normally stands guard against the sun's constant bombardment of charged particles. Now people across science communities and online forums are buzzing with rumors of a catastrophic magnetic apocalypse. Are we on the edge of a planet-wide disruption, or is the truth far more nuanced? Before we jump to conclusions, let's remember that Earth's magnetic shield has always undergone changes. Ancient rock records show that magnetic reversals, where north and south poles completely swap, happen repeatedly in the distant past. Yet talk of an approaching flip triggers waves of speculation. Are we truly headed for a sudden transformation that could upend our climate, knock out satellites, and scramble wildlife migrations? Let's explore the surprising facts, the controversies, and the emerging evidence behind the scenes of our magnetic field's dramatic journey. The magnetic field may be invisible, but it shapes life on Earth in countless ways. Think of it as a sprawling force field that extends deep into space, forming a bubble known as the magnetosphere. When charged particles from the sun race toward us at speeds of over 1 million miles per hour, this bubble flares with an electromagnetic push, preventing our atmosphere from getting stripped away. Without it, Earth's surface might look like Mars, barren, eroded, and lacking the thick air needed to host diverse life. Scientists trace the origin of this vital shield to our planet's molten interior. Beneath the crust, an enormous sea of liquid iron churns slowly in circular currents, hundreds of miles wide. This molten metal moves at thousands of miles per hour and generates electrical currents that behave like a colossal dynamo. As Earth spins, it stirs the metal like a giant cosmic blender. This motion creates the magnetic field that stretches outward from our core, anchoring us against the harsh realities of cosmic radiation. Even so, our magnetic shield is far from a perfect barrier. It forms a shape more reminiscent of a windsock than a neat bubble. On the side facing the sun, the field is compressed, while on the night side it gets pulled into a long tail. Within this extended region, 2 donut-shaped bands called the Van Allen belts swirl with trapped particles. These belts act like Earth's personal particle accelerator, capturing charged debris and cosmic rays that might otherwise bombard our planet's surface. Despite the protective function of the field, recent measurements revealed that it's weakening at an accelerating rate in some regions. Researchers have studied ancient lava flows and iron-bearing rocks to learn that such changes are not new. Our planet's magnetic energy rises and falls in complex cycles, reflecting the fluid motions in Earth's core. Yet the speed of current developments has left many experts stunned. Could our unseen defender be on the brink of a dramatic transformation? This question takes us into uncharted territory. While minor fluctuations are common, large-scale shifts, especially those that hint at a full-blown flip, raise deeper concerns. Each time the field drops in intensity, more radiation can sneak through. Even if Earth's thick atmosphere continues shielding us from most dangerous rays, our technology might not fare as well. The stakes grow higher when we consider the next big anomaly lurking just beneath our satellites. And that anomaly has a name, one that's rattling experts across the globe. One of the most debated features of Earth's magnetic field today is the South Atlantic Anomaly, SAA. It stretches roughly from the eastern shores of South America to the western coasts of Africa. In this region, the magnetic field measures significantly weaker than the global average. Some describe it as a dent in the magnetic armor, a place where shielding thins out to worrying levels. Satellites that orbit through the SAA frequently experience electronic malfunctions, sudden reboots, and data corruption. Mission operators have learned to expect disruptions when spacecraft enter the area, scheduling protective measures or temporary shutdowns of sensitive equipment. The high-energy particles that normally get deflected by the magnetosphere seem to penetrate more deeply here, posing real risks to orbiting hardware. For years, the cause of this weak patch baffled scientists. Some proposed that unusual flows in Earth's molten core create local instabilities. Others suspected leftover relics of older rock structures buried deep under the African continent. With new mapping data from agencies like NASA and the European Space Agency, the SAA has become a hotbed of research. Conspiracy theorists paint it as a sign of the imminent doomsday flip, while cautious observers see it as a natural fluctuation, albeit one that demands careful attention. Those who favor darker interpretations claim the anomaly grows wider by the day, creeping closer to land and exposing populations to extra radiation. However, most scientific measurements confirm that any increase is slow and not immediately life-threatening. Still, the anomaly's very existence raises the question: if certain pockets of the field are collapsing, is this a precursor to a larger global change? Within academic circles, these debates over whether the SAA signals is a forthcoming polar reversal or just an excursion. Excursions are partial temporary collapses in which the poles shift briefly and then revert back. They're more common than full flips and can last anywhere from a few decades to a few thousand years. The SAA may represent one such event, offering a real-time glimpse into how Earth's core might be stirring. The next piece of the puzzle lies in the restless movement of our magnetic poles, and their sprint across the globe is quite a story in itself. Long regarded as stable markers of direction, Earth's magnetic poles are proving surprisingly mobile. Scientists track the North Magnetic's pole shift from Canada towards Siberia at speeds of over 30 miles per year. That's roughly 3 times faster than its pace a few decades ago. This abrupt acceleration caught the attention of navigators and geophysicists alike. If you rely on a compass in high altitudes, the difference becomes noticeable over time. But why do the poles move? In simple terms, changes in the currents of molten iron beneath our feet can strengthen or weaken certain parts of the global field. Picture the metal swirling around in vast loops. At any moment, localized regions of flow might intensify, creating a new center of magnetic pull. Over months or years, this can shift the primary axis enough to tug the visible poles across the globe. Geological evidence from ancient lava flows revealed that Earth's field has reversed hundreds of times in the past. These flips aren't gentle. As the polarity transitions, the planet can briefly sport multiple mini-poles, with magnetic north popping up in unexpected places. Scientists have even found rocks in the southwestern United States that formed when north pointed south, an undeniable sign that flips happen regularly on a geologic timescale. An intriguing question remains, though. Do the increasingly erratic movements of the poles indicate a looming flip? Or will this pass as just another excursion? Some researchers suggest that if the poles keep drifting at their current rate, we could see a dramatic event within a few centuries. Others argue the Earth's magnetic field is notoriously unpredictable, and what looks like the start of a flip might fizzle into a milder reconfiguration. At the heart of this debate are advanced simulations running on supercomputers worldwide. By feeding data on core heat flow and Earth's rotation into complex models, experts try to predict how the field might evolve. Results vary widely, pointing to the difficulty of forecasting a process that unfolds deep underground, out of direct sight. The uncertainty fuels endless speculation, adding to the excitement, and sometimes the alarm of everyday watchers. Where there's uncertainty, conspiracy theories often breed. Let's see how these flip fears have pervaded the internet and shaped modern anxieties. Search online for magnetic field flip, and you'll find a swirl of prophecies and dire warnings. Some claim that a complete reversal could plunge us into chaos. Satellites would fry, global communications would fail, and radiation would spike to lethal levels. Others push the narrative that this is all part of a larger cosmic cycle, tied to ancient prophecies or secret knowledge guarded by lost civilizations. While such theories garner clicks and stir headlines, they often leap beyond the boundaries of credible science. To be fair, the concept of a flipping field does conjure images of swirling chaos. It also pairs nicely with age-old end-of-the-world stories that have circulated for centuries. Many doomsday theorists reference past extinction events and blame them on magnetic instability. However, upon closer examination, there's minimal evidence linking polar reversals to massive die-offs. Animals, plants, and microbes have lived through these episodes unscathed, countless times, over the planet's history. The biggest confusion arises from mixing real scientific findings, such as weakening field measurements or shifting poles, with sensational claims of unstoppable disaster. Yes, the field is weakening. Yes, the poles are drifting, but the time frame involved often stretch across hundreds or thousands of years, giving humanity ample time to prepare. Unlike conspiracies, on the other hand, frequently condense these events into a dramatic near-instant apocalypse. Another point of contention stems from the difference between a full flip and an excursion. A flip is complete, with the poles swapping for extended periods, while an excursion is a partial or temporary change. Because excursions happen more often, the planet's history is full of these near reversals, yet many sources lump the two together, creating confusion and inflating the perceived odds of cataclysmic scenarios unfolding any day now. So what's the reality? A major magnetic event could disrupt technology and cause headaches for the modern world, but it's unlikely to bring about the type of doomsday some predict. Let's now shift our focus to the very real threats to our electronics and infrastructure, threats that remain the most pressing concern if Earth's shield continues to evolve in unexpected ways. As humans rely more on satellites, GPS, and power grids, any noticeable weakening of Earth's magnetic field becomes a top-tier risk. Satellites are especially vulnerable. High-energy solar particles can damage critical onboard systems and corrupt data, causing anything from minor glitches to full-blown equipment failures. In low Earth orbit, spacecraft pass through regions like the South Atlantic anomaly, where the field's protection dips most severely. Engineers are forced to add radiation shielding or schedule safe mode operations to dodge hardware damage. Imagine losing GPS signal that guides airplanes or shipping routes. Or consider how many daily tasks depend on accurate timing signals from satellites, financial transactions, cell phone networks, and even power grid management. A more porous magnetic shield could let in bursts of solar plasma that fries sensitive electronics on a massive scale. Geomagnetic storms, already a threat, might intensify if the field weakens further. The famous 1989 Quebec blackout, triggered by a solar storm, stands as a stark reminder of the damage possible when electrical infrastructure meets geomagnetic turbulence. The International Space Station, ISS, orbits within the upper fringes of our protective bubble. Astronauts rely on the magnetosphere and specialized shielding to lower their exposure to cosmic rays. If Earth's defense wavers, missions may require thicker shielding or more conservative timelines for spacewalks. Further ventures to the Moon, Mars, and beyond hinge on stable communication and navigation networks around Earth, as well as reliable systems that won't glitch under heavy radiation. Beyond satellites, scientists worry about the global power grid. Large electrical networks can act like sprawling antennas, picking up induced currents from geomagnetic activity. Sudden surges might overload transformers or cause chain reaction failures. Utility companies at higher altitudes have studied ways to reintroduce grids or install protective devices. A consistent drop in magnetic field strength would heighten the importance of these safeguards, as weaker shielding spells more vulnerability. This is not to say we're defenseless. Engineers and policymakers are aware of the threats and actively planning, but the margin for error narrows as the magnetosphere changes. Our modern world has never experienced a full-blown magnetic flip, so there's no direct historical precedent to rely upon. Some fear we're rolling the dice with an event that might hit unpredictably. And it's not just technology at stake. Marine life, migratory birds, and even humans might feel the ripple effects of a shifting field. Several species depend on Earth's magnetic cues for navigation. Sea turtles, for example, use geomagnetic fields to guide them back to the beaches where they were born. Migratory birds set their headings each season based on subtle changes in magnetic lines of force. Whales are also suspected to tune into these signals, following submerged magnetic highways during long migrations. If the field weakens or warps, these creatures may find their routes scrambled, leading to disorientation or mass strandings. Scientists studying these animals occasionally observe puzzling shifts in migration patterns. While it's difficult to pin such changes solely on magnetic anomalies, the possibility remains that local variations in the field can confuse species that evolved to rely on stable cues over millennia. Adaptation might be possible, but evolution typically operates over lengthy timescales, and sudden magnetic shifts could pose real challenges. Humans, on the other hand, seldom rely on Earth's magnetism for daily navigation anymore. Our compasses are mostly backup tools, superseded by satellites and digital maps. Still, traditional explorers in certain indigenous communities pass down knowledge that includes reading the sky and land, in conjunction with the planet's magnetism. A drastic rearrangement might render those inherited skills less reliable. Health concerns often surface in discussions about magnetic field fluctuations. Thankfully, we're largely protected from harmful radiation by the atmosphere, which acts like a towering wall of dense molecules that cosmic rays must penetrate. The thinning of our magnetic shield could raise background radiation levels slightly, particularly at high altitudes. Pilots and flight crews might experience a minor uptick in exposure, but for the average person on the ground, the change is expected to be negligible, at least in the near future. Where we do see potential ripple effects is in agriculture, climate patterns, or even possible connections to lightning frequency. The scientific literature doesn't offer a definitive link tying magnetic fluctuations to these phenomena. Still, the complex interplay of atmospheric chemistry and cosmic rays and cloud formation leaves room for speculation. It's no wonder rumors of weird weather or spikes in certain diseases accompany any talk of magnetic crisis. The uncertainty surrounding these impacts motivate researchers and policymakers to look for strategies that mitigate risks. Let's explore how humanity is preparing, or at least how we could. Adaptation begins with awareness. Space agencies like NASA and the European Space Agency continuously track changes in the magnetosphere. Missions such as the ESA Swarm constellation offers real-time data on magnetic field strength and direction. The finer our measurements, the better we can predict when anomalies like the South Atlantic anomaly expand, or when pole drift accelerates. This data helps satellite operators plan safer orbits, update software protocols, and design stronger radiation shielding. Power grid operators are also on alert. Some utility companies install devices that detect geomagnetically induced currents, automatically shutting down vulnerable lines before a surge causes lasting damage. Frequent system checks and infrastructure upgrades ensure that crucial transformers or substations can handle unexpected current spikes. Though costly, these investments prove essential in regions more prone to geomagnetic storms like Canada's high latitudes. In the aviation industry, awareness of polar route radiation is growing. Airlines may reroute flights during major solar events, placing minimal reliance on polar paths if cosmic conditions worsen. These protocols limit crew and passenger exposure to increased levels of radiation that might arise when the shield is temporarily weaker. Scientific committees monitor solar weather forecasts in collaboration with meteorological agencies, looking for any sign of enhanced activity. Beyond hardware measures, some suggest we might eventually develop large-scale protective technologies, though these ideas remain in the realm of speculation. Proposed concepts include artificial magnetic fields for spacecraft or more elaborate atmospheric monitoring. While these are far from implementation, they highlight humanity's tendency to innovate when pushed by environmental and cosmic challenges. Still, a broad educational campaign is missing. Many people remain unaware of the potential for increased geomagnetic disturbances. Critics argue we should inform the public about contingency plans for intense solar events or prolonged anomalies in the field. The idea is not to spark panic, but to foster resilience. With better global coordination, we can adapt our infrastructure and emergency responses, thus diminishing the disruptive potential of any long-term magnetic challenges. These preventative measures only scratch the surface. The reality is far more complex, especially as we try to separate fact from exaggeration in discussion about the future. In one corner, we have sensational voices warning that Earth's weakening shield signals a near-certain flip. They say a wave of devastating cosmic radiation could sweep over the planet at any moment. On the other hand, more measured voices remind us that magnetic reversals are neither new nor typically catastrophic in a sudden apocalyptic sense. Ancient species lived through them without going extinct, and humans with our technology have ample time to plan. Sorting fact from fiction requires sifting through peer-reviewed studies and understanding the timescales involved. Even if Earth's field continues weakening at the current pace, a drastic collapse might still be centuries away. Polar wander could accelerate or slow down. The core's molten iron might shift into a pattern that stabilizes the field, or an excursion could flicker in and out, with minimal consequences for day-to-day life. The point is that we cannot know for certain, which fuels a sense of mystery and stokes endless debates. Critics accuse scientific institutions of downplaying the threat to avoid public panic, while others accuse doomsayers of selling fear. The truth likely lies between these extremes. We face genuine challenges, especially concerning satellites, power grids, and navigation-dependent animals. But a Hollywood-style meltdown is not the guaranteed outcome. Our planet's thick atmosphere remains a robust second line of defense, and humanity's problem-solving skills have risen to meet many environmental tests before. Perhaps the biggest change this time is our capacity to observe. We live in an era of satellites, sensors, and supercomputers. Data pours in from every corner of the globe, letting us watch the magnetic field's evolution in real time. This knowledge is both a blessing and a curse. It empowers us to act, but it also stirs anxiety when conflicting reports circulate. As always, the best approach is balanced vigilance, staying informed without succumbing to sensationalism. The cosmic drama played out beneath our feet is a reminder that Earth is more dynamic than we often realize. Our planet breathes, shifts, and rearranges itself in cycles that can span millions of years. That perspective can be both humbling and awe-inspiring. Earth's magnetic field is indeed weakening in certain regions, and the poles are drifting. This could herald a major reversal or simply mark another excursion on a geological timescale. Either way, history shows that life can withstand these changes, and modern science offers strategies to keep our technology safe. The final takeaway? Understanding Earth's magnetic fluctuations doesn't require panic. It calls for curiosity and preparedness. Will the field keep fading until North switches with South? Only time and continued scientific research will reveal the answer. For now, keep exploring, keep questioning, and stay alert to how this incredible planet of ours continues to evolve. Thank you for watching, and if you found this deep dive into Earth's magnetic mysteries intriguing, feel free to share your thoughts on how technology and life on Earth might adapt in the face of a changing magnetic field. Until then, stay curious about the secrets hidden within our world and beyond.